as I said, we're going to be talking about space weather. Space weather is the interaction between what's going on in the sun and what's happening on Earth. So it's outside the Earth's atmosphere, but not in interplanetary space. So space weather is what's going on in the realm surrounding the Earth, outside of the atmosphere. But it actually starts with the sun. And so coronal mass ejections. So you can see in the little animation here that this is actually a series of photographs that were taken back almost 20 years ago, showing the sun. Now, in this picture here, the sun is inside that little circle right there, and there's something blocking the view of the satellite, so it doesn't actually directly to the sun, because that fry the electronics pointed at the sun like that. But you can see the corona out here, outer edge of the corona, and then here you see a chunk of the corona that's moving away. So that is literally a chunk of the corona being thrown outwards by a giant solar flare. So a huge solar flare happened there, massive release of energy. That huge release of energy then is throwing a large chunk of the corona out across the solar system. Now, that particular one, it's going off to the side. What you don't want to see is to see it gradually getting bigger and bigger like that in all directions, because that means it's coming right at you. And so, and that sometimes happens, that sometimes you have coronal mass ejections directed towards Earth instead of off to the side. So here's from your book, a series of images showing a big blob of stuff out away from the sun. So what happens to coronal mass ejection once it leaves the sun? It continues going across the solar system until eventually it runs into something. It spreads out as it goes, and so by the time it reaches Earth, it's a little more dissipated, but it reaches Earth, and Earth is protected by its magnetic field. So we have the magnetosphere, which is the region of space around Earth that's dominated by Earth's magnetic field. And so inside the magnetosphere, you have the Earth's magnetic field that's in here, and the magnetic field in there is kind of distorted a little bit by the shape of what generically just particles coming from the sun, the solar wind going past like that. But what happens here is some of the particles get trapped in the magnetic field, and they form regions of particles running back and forth around the magnetic field that we call the Van Allen radiation belts. Because you happen to get into one of those regions where these particles are slamming into you, it's like particulate radiation. So when the coronal mass ejection hits Earth's magnetic field, it starts shoving the magnetic field around. When you shove the magnetic field around like that, then what happens is it starts displacing the inner magnetic field. And when that happens, then you have changing magnetic field on Earth. Changing magnetic fields in physics, we learn, induce various other sort of things, including electric potential, electric voltage, which then can make electric current flow. And that is one of the things that happens. The other thing that can happen is that these particles in the Van Allen belts surrounding Earth out here, these particles that are in the Van Allen belts can overload and shove down into the atmosphere, where they slam into the atmosphere, knocking electrons off of some of the atoms that are there, which then grab electrons back, give off light. That process is the aurora. So the aurora borealis is the northern lights. That's around the North Pole. The aurora australis is the southern lights, and that's around the southern magnetic pole. And so that's also happening. The other thing that can happen is all these particles slamming to the atmosphere can ionize the upper atmosphere. That can interfere with radio communications, so we can have radio blackouts. Not to mention all these particles running into the atmosphere, producing radiation loading, and so all these effects, like a huge surge of radiation, radio blackouts, and fluctuating magnetic fields, we call geomagnetic storms of various kinds. In particular, we have geomagnetic storms, radio blackouts, and radiation. Boulder, Colorado is the headquarters for watching this stuff, and at least for the United States government. And it's NOAA facility. The Space Weather Prediction Center is based there. They have satellites that are in orbit out there monitoring the sun continually. Ground-based instruments. The sun is monitored 365 days a year, 24 hours a day. And so there's always people monitoring the sun and keeping track of what's going on and making predictions as to what it's going to do and how it's going to affect Earth. As I mentioned before, we monitor the planetary K index. The K index is a measure of how variable the magnetic field of the Earth is, how much it's fluctuating as a consequence of solar activity. A K index of 5 or greater corresponds to a geomagnetic storm. So they plot estimated K indexes at various times. And so here's some plots from a number of years ago. 2010, not much activity. Then suddenly it shot upwards as a coronal mass ejection ran into the magnetic field, sort of fluctuating. And that would be a geomagnetic storm. And 2013, activity. 2014, even less activity. 2015, another geomagnetic storm, and so forth. And so, as I showed you in the previous video, currently the sun, the magnetic field is not very active at all. So NOAA keeps track of these storms. He rates them the same way that NOAA rates tornadoes, the F scale, the F number for a tornado. They do the same thing in geomagnetic storms. So likewise with radiation storms and also with blackouts. So for example, the geomagnetic storms ranked G1 to G5. A G1 storm is not a big deal. If you're on top of it, G2 is more active, G3 is more active. By the time you get up to G4 or G5, you have major disruptions with radio communications and so forth. The aurora is visible as far south as Texas if you have a G5. And I've actually seen the aurora here in Texas several times during a major geomagnetic storm. The other thing that happens is that in geomagnetic storms is you produce radio interference, and you also can produce voltages that cause a lot of current to run down power lines and pipelines, things that don't normally have DC current running down them. Solar radiation storms, they are also ranked from S1 to S5. S1 storm is a minor effect. S5 storm is major. S5 storm, for example, in 2003, caused anyone that happened to be in a transatlantic aircraft at the time to receive a couple hundred chest x-rays worth of radiation during the course of the flight. And so these S5 storms are nothing to be trifled with. Radio blackouts, R1 to R5. R5 creates substantial interaction that can last for hours of radio blackouts. And so again, during radio blackout a bunch of years ago, navigation systems were offline, and so again, this is a big deal. So the direction of the coronal mass ejection also matters as to whether we get the storm or not. On the left, that's a coronal mass ejection that's going off the side. That's not a big deal. It might hit another planet, but for us, we just watch the big storm go out. The one on the right, you can see this halo effect of the coronal mass ejection heading directly towards Earth. That's one that we have to worry about. The other thing that happens is that as the coronal mass ejection is coming towards us, it's shoving solar wind particles, which are already out there, ahead of it. And so you sometimes have radiation meters in space pick up a ramp up of radiation right before the coronal mass ejection arrives. And so that's another impact we have. Solar activity varies. Sometimes you don't see a lot of solar activity. Sometimes you see more solar activity. When there's a coronal hole, we talked about coronal holes before. So here's a coronal hole facing towards Earth right there. And that coronal hole actually allows more solar wind to come out. It also means that if there were a a flare directly under that coronal hole, you would get a massive blast of high energy radiation coming straight at Earth. You might get a little less coronal mass ejection that way, but you'd get a whole lot of radiation. And again, low activity last fall, but don't expect it to stay low activity forever. Okay. Again, I showed you on spaceweather.com how to get the current radiation X-ray measurements here, or the current magnetic activity. Spaceweather.com is kind of a good go-to place to find all kinds of space weather information. Space Weather Prediction Center, that's the official government-run website, though, and that is given this other link right there, swpc.noaa.gov. And so that'd be the official one, but spaceweather.com gets their data from there and from other sources, and so it's a very good general purpose, particularly for the lay person keeping track of what's going